everyone, welcome to Math 7195 Unit 1. Today we're going to be doing our first video from this unit on descriptive statistics. We'll cover a few topics, basic definitions, some sampling methods, the main branches of statistics, and then we'll get into some graphical methods that you will also cover in one of your labs. Well, more than one of your labs actually. So you'll all have a set of notes that look like this. They are posted on the Learning Hub. And I'm just going to go through and kind of annotate and talk about them as we go. Future lectures will have more open space for writing and solving problems. But this first one, we have to get through the business of, basic definitions and such. So there won't be a lot to write today. First, we should maybe say, what this course is about. We're talking about statistics. Statistics is both a branch of math and they are individual values that summarize a data set. I peeked at a few different textbooks and found a few different definitions, and I just kind of merged them together until I found a definition that sort of covered everything. Statistics is a collection of methods for planning experiments, obtaining data, and then organizing, summarizing, presenting, analyzing, interpreting, and drawing conclusions based on the data. A lot of math students don't exactly love some of statistics because we don't always have concrete answers. When you're taking calculus and differential equations, you get your nice solid answer and you circle it and that is the answer. You check the back of the book and you know if you're right or not. In statistics, things tend to be a little fuzzier, and that makes it a little tougher for some of us to swallow, at least at the beginning. But eventually you will start to embrace this, where you'll get your answer and then you'll have to explain it. And that will be probably the most important part of this course, are explanations rather than just the rote calculations. In engineering, there are many uses of stats. I just made a little list here. Sustainability. And my mining students look at core sample studies. We can look at material reliabilities, designing things for extremes. Oftentimes we're looking at material strengths, or if we're in a manufacturing field, maybe we look at producer and consumer risks when analyzing, assembly line type data. Much of statistics can be summarized with the following very crude little diagram here. Basically, we have large populations that we need to study. It's too expensive or too difficult to study the entire population, so we take a subset of that population called a sample. We study the sample, and we hope that the sample gives us enough information that we can make generalizations about the overall population, and it won't cost us as much as trying to study the whole population. When we're studying the entire population, or look at attributes of an entire population, we call those numbers parameters. And when we're studying samples and come up with numeric summaries, we call those things statistics. Usually we'll use Greek letters to indicate parameter values, and we'll use our regular alphabet to indicate statistics. So we'll have to make sure we use the correct notation as we go along. Examples, when we're talking about the mean of a population, we'll use the Greek letter mu. And when we're talking about a sample mean, we'll use a typical, alphabetic letter with a bar over it. X bar for the mean, or mu for the mean of a population. The little picture we had up above gets repeated here, a little bit more detail, where we have some population. We'd like to know something about it. And then we need to come up with some way to take a subset from that population, call that our sampling procedure. That could be many different ways, sometimes drawing names out of a hat, sometimes taking every fifth item in a list, and there are many other ways. We'll talk about some of them. Once we've decided on a procedure for our sampling, we'll study that sample, summarize it either numerically and graphically, and then we move on to another branch of statistics called inferential statistics, where we use probability. We link probability to our data to come up with predictions and decisions, and we can kind of quantify these values with some degree of precision. We can estimate the probability of our error, for example. Why do we do this procedure? Why don't we just always study the population as a whole? Well, it's usually just time and money is the main reason. Other times we have to test things, and during the test we're destroying things, or maybe we have test subjects and there are only so many available. And other times we have infinite populations. If you're studying water molecules or something like that, they're essentially infinite number, so you can't study them all. I mentioned that we had different sampling methods. The most common one is the simple random sample, essentially where everybody in the population has an equal chance of being picked. This is drawing names from a hat or picking numbers out of a, what's a phone book anymore? I must have stolen that from a textbook. That is one of the more preferred methods of sampling if you can achieve it. Other times we'll look at methods of maybe stratified sampling, where we want to make sure that we have enough, say, young people represented and enough old people represented, even so we'll break the population up into various strata, and we'll take a sample from the young people and a sample from the old people and a sample from the middle-aged people. Or maybe we could break our sample into two groups of men and women and then study them. Another method is that systematic sampling. I mentioned this one where if you're looking at assembly line data, Amazon takes a look at every 10th package to see if the box is damaged. The next form of sampling, and this is just a small list, there are other methods, is cluster sampling. It's maybe a more convenient way of sampling to try to get a hold of people. An example here is an airline is trying to find out if people are satisfied with their flights, and rather than talking to 3 people on every flight, they'll just take one whole plane and check everyone, and then grab another plane and check everyone. It might be just a simpler way of doing the sampling for them. And then there's the convenience sampling, which is often the worst, where you take existing data and you start studying that. And this is often done because of cost. You'll hear things like, coffee drinkers tend to have a lower chance of getting diabetes. And you'll see a news report on that. And they'll even say that it comes from a Harvard study has shown that coffee drinkers have a lower incidence of diabetes. Oftentimes those studies, they stole the data from Harvard, sure, but it wasn't necessarily the intention of the study. They may have been studying something else, but they asked the respondents, hey, do you drink coffee? And they noticed some sort of correlation between variables, and then someone reports on it. This is convenient, but it's not a very controlled way of doing things. When we are sampling, we have two forms of error, the sampling error and non-sampling error. Sampling error is the one that we can't really control. It's the difference between the true population value and your sample value. In our class, maybe I'm interested in the assignment 1 results. Say I've marked 30 papers out of 36 students, and I just can't wait to be for the final results, and I calculate the mean of those 30 students. The mean of those 30 will probably be pretty close to the mean of the whole group of 36, but it won't be exactly right. So the difference between my sample value and the actual population value is the sampling error. Now, other errors occur. We call those non-sampling errors. This is when you actually make a mistake. You write the numbers down wrong. You have a biased sample. I want to know the mean of my students on assignment number 1, and I just mark the students in the front row, and then I calculate the mean of those students. Well, we all know that the front row is full of the smartest kids, so certainly the average there would be maybe higher than what it would be for the entire class. So I've come up with something that's biased. There are many other errors that we could conduct or could make. We'll try to discuss them as we go through the course so that we can avoid them and so that we can be critical of others. There are a few branches of statistics. We start out the course discussing descriptive statistics. That's basically much of what Unit 1 here is all about, where we're mostly summarizing data and collecting it, coming up with different ways of organizing it. We're not looking too much at the interpretation as much as just the raw collection and organization. The next unit that we cover in this course and in many courses is then probability, where we start out with games and lotteries and such, and then we find a way to apply probability to the more realistic situations of data collection and summary. And then we put those two units together, and we have this thing called inferential statistics. And this is where we make conclusions and decisions based off of our data. We do hypothesis testing and confidence intervals and all those sorts of things to help draw conclusions about the data that we've collected, and hopefully we can say something about the population without necessarily having the entire population. Other things that we can do in statistics are, study reliability. We can talk about quality control, curve fitting and least squares. So there are lots of different things we can discuss, and in this course we actually do cover quite a broad variety of these things. By the end, we'll have a pretty good sense of the basics of statistics. In the descriptive statistics category, we have our summary methods, and typically we have numerical summaries and graphical summaries. I thought we would start out the lecture here with some graphical methods. I made a little list here of some of the common ones. Bar charts, pie charts, frequency histograms, ogives, stem and leaf plots, scatter plots, and control charts. Those are plots over time, often used in quality control situations, but in other places as well. I believe we have a lab on that fairly soon. I thought I'd do a couple of these in the lecture notes here, and then you will do a few more in the lab setting. The stem and leaf plot, you'll see that long paragraph trying to explain, what a stem and leaf plot is and how to create one. But basically, it's a plot that helps us see the shape of our data. We'll go through an example, and then you'll see how this works. We have our example number 1. Namzor Enterprises is interested in the length of time it takes to assemble some trusses. To do that, they studied 15 random assemblies, and they monitored how long it took to, build the truss. The data is given here in minutes. So the first truss took 95 minutes, the next one took 96 minutes, the next one took 97 minutes, then 81, and then 94, etc. It looks like there are 15 values there. I noticed that those values range from the 80s to the 160s, and I made those tens categories what we call the stems. So 8 is a stem, indicating 80s, 90s, hundreds. We're going to translate our data into this now by adding the leaves. So our first value in the list was 95. So I'm going to, in the 90s category, I'm going to write a 5. The neater you write it, the better graph you'll have when you're done. The next one is 96, and then 97, and we keep going, trying to draw our numbers roughly at the same scale. The next one is 94, so that goes in the 90s, and 81, and we just continue on populating this. We have 98, 99, 100, 128, 168, 169, and then we have the rest, 101, 102, and 119. What we get at the end of this is a rather crude-looking histogram. If we look at this thing on its side, kind of making a mess out of it now. Maybe if I change color pens. You'll see that we have a nice bar chart. Now this isn't a very professional looking bar chart. This is the sort of thing you might scribble in your, field journal, or, in your, when you're working in a lab somewhere. As you're collecting data, it gives you a rough idea, and a quick rough idea, of the distribution or shape of your data. What we can quickly see with this data is, most of the values are in the 90s. We can also see, other features like, hey, 168 and 169 are rather unusual. They stand out against the rest of the data. Why did it take so long to build some of those trusses? Should we investigate? Should we, retrain an employee? Should we fire someone? So by just such a crude little graph, we can quickly see some nice attributes that we might not see by just looking at, just the group of individual values, especially if they're not sorted in any way. So this is a nice little graph. I wouldn't publish it in your next, research report, though. Again, it's just a crude summary to give you an idea of what's going on. The next type of graph is a little bit better, a little more professional. We'll call this a frequency histogram. And this one works because a lot better than the stem and leaf plot because it will handle larger data sets. In our stem and leaf plot, if I had 80 values, my plots would start to get to be so long in the horizontal axis that maybe I wouldn't be able to see anything. And I also sort of limited in the way I group my values into groups of tens. Here I have some data where we looked at the daily emissions from an industrial plant. This is sulfur oxide, and it looks like the data is in tons. We have these 80 values here, and when I just look at a field of 80 values, it's hard to really identify, any major features. Where's the middle? What's the most commonly occurring value? Are there any unusual values in that group? What shape does it make? But if we make this thing called a frequency histogram, we can summarize it quite nicely. I made a little table here where I made classes. My first class I decided would be a width of 4 units wide from 5 to 8.9. And then the next one was also the same width from 9 to 12.9. So each one is 4 units wide. I make sure that they don't overlap each other. And I make sure that I make enough classes such that I capture all 80 values in my list. So I kind of scanned through the list and I saw that I didn't have any values under 5, and 5 was a nice number, so I started at 5. Why did I make them 4 units wide? Just because I could. I probably, more naturally would have made my first category from 5.0 up to, say, 9.9 and made them all 5 units wide instead, but hey, I'm a rebel. It looks like I made my my classes 4 units wide. A way to kind of come up with this might be to find your maximum value in your list and your minimum value in your list. Find the difference between, and then say divide it by 8 or 7 or 10 until you get a width that you like, and that will give you the number of classes that you'll end up with as well. You can kind of fiddle around with it until you get a plot that looks good. With these things, software makes this not too hard to create, so you can sort of play around with it until it looks good. Just make sure you follow a few rules, that your classes don't overlap, that you cover all the data. I mean, that's the main rule. Once you have it set up, your classes set up, go and count. How many values are there? In the range from 5 to 8.9, we go and scan through our list and say, okay, I see a 6.2, a 7.7, and can I find, there's a third value. There are 3 values in that range. And then you continue on and do it for how many values are between 9 and 12.9. Trust me, there are 10. Luckily for us, software will do these counts for us, so we're not likely to make many mistakes. So if we add up all these frequencies here, we should have a total of 80. The table itself is, rather interesting, but if we make a plot of this table and call it a frequency histogram, we put the classes on the x-axis and our frequency on the y-axis. Plotting this thing to a nice scale, you'll see I started at 0 to not deceive anyone. We get a nice picture here. We see that it has sort of a classic, bell curve shape. We can see where the middle is. We can see what category has the most values. What is the most likely emission? Somewhere between 17 and 21. We can also see that there aren't any, real extreme values in our list. Nothing really stands out. So this is a really nice way to make a plot when you have, especially the technique we just did with 80 would apply to if we had 10,000 values or 100,000 values. My title here is poor. I probably shouldn't have given this a title of frequency histogram. I was teaching you about frequency histograms, and that's why it has that title. Generally, we should have this title say something like, daily emissions from our plant in 1999 or something like that. And then we need to label our axes to indicate what they are. I did a nice job on my x-axis. And my y-axis I did okay too, but my title there is definitely poor. definitely do try to strive for better. I find more words is generally better than fewer. When I reading a paper, I tend to look at plots and graphs and things long before I read any text. So when I look at a plot, I'd like to be able to figure out what it's about without having to read some paragraph beside it. So a longer title will often help your reader out quite a bit. Another type of plot is a relative frequency histogram, and you'll see in the picture it's exactly the same as the one we just had. The only difference between this one and the one we had before is I plotted percentage on the y-axis instead of the actual frequencies. To convert all those values to percent, the first class there had a frequency of 3. There were 80 in total, so that's 3.75% of all the data. When you add all those percentages up, you better end up with 100%. Now when I make my plot, I get the same shape, so I still see where the middle is. I still see the overall shape. I don't see any major outliers or anything. So why might we do this? Generally in comparison situations. If I need to compare the plant's emissions this year to the plant's emissions next year or a previous year, maybe not every year I have the same number of data points. If I collected 80 points of one year and 30 points another year and 150 points another year, to compare them, I can keep them all on the same scale if I, convert them all to percentages. And then we're moving on to another way to summarize that same data is a cumulative frequency table or cumulative relative frequency. In this table, we already had frequency and we already had relative frequency. Now I'm going to do cumulative frequency. In the first category here, there are 3 items. In the next category, I'm going to add 10 plus 3 to get the 13. And then in the next category, I'm going to add the 14 on to get the 27. And then in the next category, I'm going to add 25 on to end up with 52. And you keep going with that. Add 17 more, add 9 more, add 2 more, and in the last category there, we have all 80. In this case, we're basically building a less than or equal to table. How many values are less than or equal to 8.95? How many values are less than or equal to 12.95? And you notice I defined a new term called class boundary, which is just the value that's in between the two classes. It's a value that we can't ever land exactly on. That way we eliminate the whole problem of, is this a less than or equal to situation? We can always simply say it's less than, because we'll never be equal to 8.95 because our data was all rounded to 1 decimal place. So it's just a way to make sure you never double count a value. We can then make a plot of these cumulative frequencies, which we could also convert to, a plot with percentages, just like we did with the histograms, and create this thing called an ogive. So I plotted the 3 and the 13 and the 27 and the 52 and the 69 and the 78 and the 80. And we get this ogive. It's nice if you're asking questions like, how many days were emissions below 15 tons? Well, I can go to my plot and even do a little interpolation. I can find 15 here. And say, I think that emissions were around 20, or how many days, I guess I'm asking. Number of days would be 20 days. This is out of 80, if you recall. So 20 out of 80 days emissions were 15 tons or less. Maybe a more interesting question would be, how many days were emissions under, say, 30 tons? Maybe some federal agency says you must keep your emissions under 30 tons. Otherwise, you are worried about getting a fine or something. So again, we could answer that question by just going on our graph and going up to 30 and, making an estimate. And in this case, it's pretty close to 80 by eyeballing it. So we aren't going over 30 very often. And that's our ogive. We're going to talk about other plots in our lecture, especially plots over time. We'll add basic bar charts where we have categorical data. We'll do some pie charts. I'll have you make those things in a lab. I think a hands-on approach to some of them is good. I think that's a good place to end this video, and we'll continue on with other descriptive statistics in the next video. Hope you have a great day.